Hi everyone. So let's now see the solutions of these questions. So let's see this question. So in this question they are saying that you have your usual loss function, but instead of the usual regularized function, they are multiplying with the diagonal matrix D. Okay, fixed diagonal matrix chosen by the user before training, right? The term bias is not regularized. That's fine. Suppose the feature 1 is less reliable than feature 2. Hence, we want the model to assign a smaller weight to feature 1. So, they want the model to assign a smaller weight to feature 1. So, firstly, let me just, open up this D. Okay, there are two features only, I think. Okay, feature 1 and feature 2. And let me just open up this D, I mean D1, D2, and let me just see that what happens if you have this and then if you multiply with the D. So, W transpose DW will be D1 W1 square plus D2 W2 square. Now, if you want to give less weight to D1 or to W1, which means to the feature 1, which means W1 should be lesser, which means you penalize this more, then only it could be lesser. So basically, you want D1 to be more than D2. Okay, I mean the more it will be, the lesser W1 will be. Okay, so I can say penalize W1 more. Okay, so the corresponding weight, which means the corresponding number that you are choosing with respect to W1, okay, that is chosen before the training. Okay, that's what they are saying, right? So this should be more than D2. So D1 should be more than D2. Should not be equal, should not be 0, it should not be the case. So A is the correct answer here, right? Easy question. So you can say for this question, A is the correct answer. Okay, so this is the question, and that's very easy question. So finally A will be the correct answer. Now let's just move to the next question. So in this question they are saying that some loss is defined, right? So loss is defined in a piecewise function, and then A and B values are also given. The model is evaluated on these 3 points. So they are saying what is the average loss. Okay, so what you can do, you can basically find out the predicted value. Predicted value is basically using 2x. Okay, so using this 2x you can find out the predicted value, and the original value is anyway right, 3, 5, 4. These are the original values. Now based on this comparison, right, if bi cap is greater than or equal to y, then you will be having 2 into bi cap minus y. Okay, if bi cap is less than y, then you will be having 1 into. Okay, so let me just check if bi cap is greater. So bi cap is greater in this case only, so it will be 2 into bi cap minus y, which is 2. Okay, otherwise it is 1 into bi minus y cap, right? So 1 into 1 into 1. So I think this is 1 plus 1 plus 4. Okay, so 1 plus 1 plus 4, these are the 2 times 1 and then plus 4 divided by 3. So which means 6 divided by 3, which means 2 must be the answer. Okay, so let's check. Yeah, so this easy question only, you just need to apply the definition of loss function. Now let's see this question. They are saying that given n linearly independent feature vectors in n dimension, each assign a label plus 1 minus 1, consider linear classifier of the form sin of wx. So you are going to check sin of wx, right? So see here in this case, which means whatever the sin of wx, based on that you will assign. So let me first write all the let me write in this form. So basically all the features are linearly independent. That's what they are saying. Let's suppose this is a data matrix and this is, let's suppose, corresponding W, right? Now you will take the sign of xw, which means this is, let's suppose, x1, the first data point. Okay, this is the data point 1, this is the second data point. So since all the features will be in the column, since all the features are linearly independent, so I mean if they're n cross n matrix, let's suppose, okay, the matrix dimension is not given, but that's fine, n linearly independent features in n dimensions. Okay, so you have n features in n dimensions. Okay, so so basically these are the data points here, right? Now this bi, okay, the sign of this you need to check. So this is basically yi, right? I mean you can assign based on this, it could be positive or negative value. You can assign minus 1 plus 1, I mean based on the yi values, right? So it will be either plus 1 minus 1 depending on the sign, the multiplication of this. Now since this is the, you can say that all the features here are linearly independent, so that's why this matrix is basically, you can say, a full rank matrix, right? A full rank matrix. That's why you can choose any bi here. You will be having a solution to any bi. Okay, so we will have solution. You don't even need to worry about the sign. You can have the absolute values. Okay, you don't even need to worry about the sign. You will be having solution to any bi you take here. Okay, any bi. So we will be having solution to any y here, any y. So which means you can, there exists a w, okay, I mean there must exist a w, and you can have any y here, there will be a w correspondingly. So for any assignment of +1 -1 level to n point, there exists a weight vector w to correctly classify all the points. So that's why A is the correct answer here. Understood? Such a linear classifier can correctly classify all the points and all the points on the same level and all. So all the answers are wrong. So basically A is the correct answer, because you can have any y here, there exists a w. Okay. Yeah. So answer is A. So since n feature vectors x1 to xn are linearly independent, so they form a basis. So basically you can assign any label and you will be having the answer. Now let's see this question. In this question they are saying that given this data, which of the following is true? Okay. So now if you notice that for the same data point you have plus and minus both. Since for the same data point you have plus and minus both, so it doesn't matter whether you are having linear classifier, quadratic classifier, non-linear classifier, whatever you do, you cannot basically you cannot achieve the 100% accuracy, because for the same data point you have minus also, so for the same data point you have plus also. So no deterministic classifier based on x1 x2 can achieve 100% accuracy on this data set, because for the same point it is plus and minus. Okay, very easy, simple. I mean for this this DPP all the questions are quite simple. This question is asking about L1 and L2, right? So whether L1 is making the coefficient to 0, okay, exactly 0, or L2 makes them small or something like this. So we already know that L1 okay, by the way, here it is little confusing. Here L2 is actually the L1 regularization. I mean L2 is the loss function name. So L2, okay, so you must say that here, I mean let me just write in L1 L2 form, I mean the regularizer form. So basically here this will increase to exactly 0, this will increase to small weights. Okay, that's what we already know. So why, I will just tell you. Okay, why I will just tell you. So I can first, let me select the answer. L1 takes to know, L1 generally makes a small but not L2 makes the coefficient exactly 0. Yes, so B is the correct answer here, right? Based on the convention. Okay, L1 and L2 are the loss function names, right? So that's why B is the correct answer, because L2 loss function or the below loss function is actually using L1 regularizer. So basically L1 regularizer, okay, which is lasso. So L1 regularizer can make the some coefficient exactly 0. Okay, so this is the regularizer name. Okay, not the loss function name. So sorry, the answer, actually this is a bit confusing. The answer is B only. Sorry, answer is B only. Okay, so L1 generally makes this small. I mean L1 is loss function, it makes it small. So by the way, let's not worry about L1 and L2. Let's talk in terms of the regularizer only. Okay, so L1, why you think that L1 regularizer makes the exactly 0? I told in the lecture also that why L1 makes exactly 0 and why L2 doesn't. L2 is not really interested in exactly 0 but makes it small. So if you remember that I told you that if some value is very close to 0, right? Not exactly 0, but if you take the square of it, then it is so small that L2 loses the motivation. I mean if you take the square of W square is so small that L2 loses the motivation to push it further down, right? But for the L1, this is just X, so L1 still have the motivation to make it exactly 0. Like in the lecture we have seen in the very good detail, but let me just remind you that I told you that in L2 we don't have the enough motivation to go to 0, right? And in L1 we have the motivation because L2 just pushes very very close to 0, and then because of X square, right? But L1 is still here, so L1 tries to make it exactly 0. Or in terms of the gradient descent also, I try to explain you. See, by the way, this is L2 square, this is very very, I mean close to 0, but here it is not close to 0, it is, the penalty is more, so that's why you make it 0, right? But in terms of the gradient descent also, I try to explain you that if you have some loss function, then if you have the gradient descent, if you are having the let's suppose L1 regularizer, okay, for the L1 if you keep on applying the gradient descent, because it's an iterative algorithm, then it will be just, for example, if this value is 1/10, then it will minus 1/10 minus 1/10 like this, right? Again minus 1/10 minus 1/10. But here it is coming out to be W into 1/10. So if W is initially 1, let's suppose, then 1 minus, after 10 times it will be exactly 0. But after 10 times it will be 1 upon 10 power 10, something like this. Not exactly 0, but very close to 0, okay, in terms of L2. So the reason, if you have not understood, that's fine, because that gate might not directly ask the reason, but you must know that L1 pushes to exactly 0, L2 pushes to close to 0. Okay. In terms of the, if you remember, in terms of the geometrical interpretation also we have seen this. Okay. If this is your loss function, then L1 actually touches something like this. I mean, it's a diamond shape or the or something like this. So L1 basically touches some of the ways to exactly 0, but L2 basically touches, okay, if something like this, then L2 touches to, no, I mean close to 0 but not exactly 0. Okay, so we have seen these kind of things also. But yeah, you must know this, that L1 actually make exactly 0, L2 make near to 0 but not exactly 0. Okay, I mean L2 can also make exactly 0, but L1 make it more. I mean L1 is basically more motivated towards making it exactly 0. Okay. Yeah, so that's all. Thank you everyone. These are the solutions for this DPP. Thank you.